I agree with that. I think that's why they were
It was like right, it was rice, and it would go, no, I mean, like, guys, it was like rice, but it was rice.
I don't know, it's called, I remember we were
It
like.
was salty, it was salty, yeah.
Yeah, then I remember.
All.
One of my friends.
Yours, brown and white.
It's on me.
So,
like. She's very good, like, widely available.
I want to just revisit worksheet 1. I think number 6, there was that problem where we had to involve arctangent, and then plugging in and evaluating. It did feel like having to understand what the arctangent graph looks like. And I want to just kind of give you another way of thinking about this problem, basically without using arctangent graph and just using the knowledge of your tangent graph. So if you remember tangent graph has asymptotes at -π/2 and π/2. And if you get to this stage here, then you're basically saying, okay, 1/3 arctangent of infinity. So another way of saying that is this arctangent infinity means when is tangent of theta equal to infinity, right? And tangent is equal to infinity at the asymptotes, but -π/2 is not inside the interval. So π/2 is what makes sense there. So I just want to give you another way of thinking about this problem without feeling like, oh, I have to have my arctangent graph figured out to evaluate that. I can also look at it from the tangent's perspective if you can convert that arctangent to be, oh, that's just tangent of theta equals infinity. Same thing here. Arctangent of 0 means tangent of theta is equal to 0. What theta will allow tangent to be 0? And the answer is 0. Just highlighting the last few problems here involving L'Hopital's rule. So number 10, anytime I have a variable raised to a variable or something raised to something, we know that those are all considered in indeterminate form. So in that case, we are going to work with that base raised to the exponent in a different form. So we're going to start off as saying, okay, I'm going to start off with y is equal to x raised to the x squared. Let's get that x squared to come down. To make that x squared come down, I'll take the natural log of both sides. And when I take the natural log of both sides, then that exponent is free to come down using product property. And now we're not trying to find the derivative here. We're just trying to get this right side to be in the form where we can apply L'Hopital's, because ultimately we're trying to find the limit. So to force that x squared to come down to the bottom, we're going to make it divided by 1 over x squared. If I divide by 1 over x squared, then I can just think about, okay, what is the limit as x approaches 0 from the right side for this expression? And to do that, I'm just going to be, well, first, if I plug in 0 into the denominator, 1 over 0 is undefined. So we got to kind of continue thinking about what is happening there. If I plug in 0.1 or 0.001, as I get closer towards 0, decimal wise, that means my denominator is getting smaller. If my denominator is getting smaller, that means overall my fraction is getting larger and larger towards infinity. And here, limit as x approaches 0 from the right side of 0 of natural log of x. If you think about what natural log of x looks like, here's natural log of x graph. So if I'm approaching, so if I'm approaching 0 from the right side of 0, that means my natural log of x graph is going in this direction, right? And as I get closer and closer towards 0 from the right side, that y value is getting closer and closer towards negative infinity. So for negative infinity or positive infinity, this is indeterminate form that we can apply L'Hopital's rule And once we know that we can apply L'Hopital's rule, I'm going to get that denominator ready. So make it x to the -2, and now do derivative. So natural log of x is u prime over u, or 1 over x. X to the -2 is -2x to the -3. Clean that up, get this fraction as clean as I can get, and then I'm down to x squared over 2. Evaluate the limit as x approaches 0. If I plug 0 in, I get 0. That's a real number. So the right side is equal to 0, but I'm still having to think about natural log of y on the left side. I'm just trying to solve for y now. Raise both sides with e as the base. Y is equal to 1. Okay, 11 and 12 follows very much the same idea here. Variable raised to the variable. So take natural log of both sides. Once that exponent comes down, then try to figure out how can I get a numerator denominator to show, and then evaluate the limit. Let's see if we can prove that it's infinity over infinity. It does. We can do derivative of the numerator denominator, clean up that expression, reevaluate the limits, and if it gets you to a real number, then we can stop and figure out how to solve for y, getting it out of natural log. Uh, 12, same idea. Variable raised to a variable. We'll take the natural log of both sides. Um, 1 over x comes down, and 1 over x is already nicely can be nicely put in the denominator without doing a lot of rearranging. So evaluate the limit, we get 0 over 0. That is a condition for L'Hopital's rule. So find the derivative, numerator denominator, reevaluate, we get 0. Natural log y equals 0. Exponentiate both sides, y is equal to 1. That's our limit. Okay, 13 and 14. We're just handling our arc-length formula. So length of a curve, integral a to b square root of 1 plus f prime of x squared. So we just have to find f prime, and then put it into the arc-length formula. 13 is only asking you to set it up, and same with 14. So pretty straightforward once you can, if you know the formula, if you know, just have to find f prime and then match or indicate the setup. Okay, so today want us to work on worksheet 2. If you were unable to show me the result of worksheet 1, maybe you can finish worksheet 1 and show me so I can give you credit there. But otherwise, I'd like for you guys to start worksheet 2. Right, so as you're working through, let me know if you have any questions. If you're stuck on any parsing problem.
Well, I think, I mean, this is my answer here, but I have to still evaluate this, right? Because I evaluate my balance.
Yeah.
So I'm just plugging 7 2 into this expression. Okay, so this is my, I mean, this is not quite good, but
Yeah.
after I get my derivative, I still first want to see the function. But, sweet. Yeah. This is here, this here. It's that plus 0 and 4x. I get 0 over infinity. That's basically really small. It's basically 0. This is small. It's so too bad. Oh, yes. Oh, basically, I wiped out the 1 and I treated my numerator denominator as 2x over 1 plus 2 like this. Yeah. So then I found my derivative. Oh, sorry, it should be 2. I think that should be 2. Okay. So it's 2 over infinity. That's still going to be 0. But yeah, okay. I should have put 2 down here, right? Because if I plug infinity into for b, it'll be negative. Find out this absolute value. So yeah, you're right. Yeah, negative. We have positive. I got a equals 3. Oh, a equals 3. Yeah, what is? Yeah, you can see.
It's you just alternating from positive and cancel out.
Well,
Just be.
Mike, let me look at that. I think,
Guys, my key may be wrong for number 5, so I'm gonna work through it again. Okay, let me walk through number 5. Sorry, the key is wrong. Thanks for catching. 5 on worksheet 2. Okay, so first, I want to look for any discontinuity. There's discontinuities at 0 and 1 because of the denominator, but these have no impact because let me pass. Yes. Okay. Okay, so there's no impact in terms of additional discontinuities that we have to worry about because these are outside of our interval. But we still know we got to deal with this issue. So I'm going to take the integral of this improper integral here from limit as b approaches infinity. But I know to take this integral here, this feels like it could require a partial fraction first. So we'll start off with partial fraction. So a over x plus b over x minus 1. Identify the factor from each denominator and then go through the cover up method. So here I'm going to cover up the x, 3 over 0 minus 1. That's -3. So my a value is -3. X minus 1, set that equal to 0. X equals 1. I can cover up the x minus 1. 3 over 1 is going to be 3. So my a is -3 and my b value is 3. So we can go ahead and set that up and expect things to work out from, we know this is just the straightforward integral natural log problem. So 3 over x becomes 3 natural log of absolute value of x. And then 3 over x minus 1 becomes 3 natural log of absolute value of x minus 1. Now that negative there, I'm going to rearrange it. I'm going to have that first term come first, that positive term come first. So 3 natural log absolute value of x minus 1 minus 3 natural log of absolute value of x. Now, especially if we're dealing with improper integrals, I think it really helps to see the relationship if we can use log properties to condense. So natural log of a minus natural log of b is equal to natural log of a over b. So if I can rewrite this in this form, it'll be easier to interpret what's happening with infinities when we're dealing with limit as b approaches infinity. So I'm going to plug b in first. So 3 natural log of b minus 1 over b minus 3 natural log of 1/2. Okay, 2 in for x, I get 1 over 2. Now, let's do limit as b approaches infinity. Now, I have my, this is basically infinity over infinity. Now, you see that this is basically involving, if you think about limit as x approaches infinity for degrees that match, we know the degrees match, this will just end up giving us what within this absolute value. Just 1, right? So that's good because we know natural log of 1 is 0. So that converges. So we know that's safe. So this is the only thing that could be causing an issue in terms of giving us a diverging solution. But 3 times 0 is 0. That converges. Just have to worry about what's happening here. So I'm just left with -3 natural log of 1/2. So that's an acceptable answer. But sometimes on the AP exam, if they clean this up even further, what they would do is they would pull that 2 up to the top and make it 2 to the -1, bring that -1 down and make it 3 natural log of 2.
Get natural log of 1 back at like at the top. Yeah, 3 natural log of B minus one over B, I should get natural log of one.
Right, so imagine you're just doing this operation there. Limit as B approaches infinity of B minus one over B. What's that equal to? If my degrees match, right, if we're doing X approach infinity or B approach infinity, we compare degrees, right? Degrees match, then we should take the ratio of the coefficients.
Oh,
Right, ratio coefficient is one, so that becomes one. And so therefore natural log of one is zero, so I would put that here.
yeah, I just forgot about that.
Right, yeah, so we have to kind of, we didn't quite do something exactly like this before, so I want to make sure. Yeah, thanks for catching that first of all, and then that allows us to, because if we didn't, condense, then it's hard to see, wait, what's infinity minus infinity? It's hard to know what that relationship is. But, to get it is, using quotient property, a lot easier to realize what's happening. And are we good with this connection here? Now, if it's free response, this is completely a legitimate answer, but if it's multiple choice, sometimes they may clean it up even further, and I want you guys to see the connection between these two. Issue worksheet, yeah. Okay, good, mark it down, thanks. Thank you.
I got another. But I'm wait, on this, we need to do some, when it's time to vector, we will be doing DT, but like.
What he did is just factor out the C prime. And so you don't have to solve for the pre prime when it's zero, you just factor it out and then all it. Like, you know, when you solve an equation like x squared minus x, you factor out an x and then x times. Because you factor out the p prime and solve it.
Oh, no, because it's before the.
Yeah. You can do all the total. Okay, yeah. But if it's zero, you solve it, so it gets something there, also it's there. That's it. Okay, that's good.
See, it's. This thing's how you don't. What was right now?
So basically you just substitute the x and then you multiply it by whatever the derivative of that top function. So if that had a number, like 4x.
No, what if it was like, you know, it's like one.
Oh, just one, and you have to take your derivative, since it would be a constant, it would just be zero.
So it would just be this.
No, it'd just be zero. Like if you have the derivative of 0 to 2, that's not function. They take the derivative of that, that'll just be zero.
So you want to get anything.
Yeah, that's why there's always a screen function. Over it, if you want it.
It's in this one. So one. X, so negative sum.
Yeah, if there's more class times, plus it's gonna be the pattern that we don't have still plus minus. So to get it out. It looks like the, so they want the perimeter of this kind of semicircle. It's all temporary. Well, they didn't really want to go being calculated, but just by looking at it, you can see that you want this part of the perimeter and you want this part of the perimeter. So you take the distance between the two of the circle, and you're always not saying that this one is just negative to that distance between every four. So it's four. Four. Plus, well, whatever the distance. Is to find this distance, you just take clear of the square. I don't really like to go for them thing. I'm trying to like, I'm it's like my so, here, so, which would be fancy. I don't sell it. I don't know if we can buy it. Because a lot of it, each easily go with it, right here. Yeah, that's the only way.
Okay, so your homework is to finish worksheet 2, and I'll check it Wednesday after you guys get back from break. Okay, go get your phones.
I think is show up in the journal, but if you have your tracking of limit that results in 0 over infinity or infinity over 0, do you lock the calls off of that, or do you have to make it?
Yeah, it has to be either 0 over 0 or plus or minus infinity over infinity. 0 over infinity is not quite form that we can use for low balance.
How do you use the broad? A lot of answers, a lot of buttons, but. But I think that. Probably looks like it's the double. It's a very electricity things over. That's why we don't expect a pressure established. She goes, wait, so